Okay, patient SM lost her amygdala on both sides. Okay, she cannot experience fear. She doesn't recognize fear on facial expressions of other people, and she doesn't experience fear herself. Okay, and so that's the striking piece of evidence on what the amygdala does. Her face recognition is normal, recognizing identities. Her IQ is normal. She's overly trusting of other people. Okay. Okay, so that's all you need to know about the amygdala for now. Okay, let's talk about white matter. Just brief review. Here's a kind of tunnel through a piece of cortex. Okay, so my brain cortex is wrapping around like that. If we took a piece like this, just took a segment out like that, this is the outside of the brain up there. Cortex runs like this. And gray matter is the stuff on the outer surface that's full of cell bodies. Okay? White matter are the axons, the processes that come out of those cell bodies and travel elsewhere in the brain. Okay? Everybody clear on that? Okay, so we got gray matter up here and white matter down there. Mostly myelinated axons that have that layer of fat to make them conduct fast. And so you'll see bundles of white matter in the dissection. And so here's an actual picture, photograph of the slice through a brain. So all that white stuff up there is white matter, okay? And so you might say, well, that's just a big bunch of wires. Who cares about that? It's a good question. But actually, the wires are pretty damn interesting and pretty fundamental. And so I'll just give you a few reasons, and you don't need to memorize every one of these. I'm just trying to give you a gist of why we might care about this, and then there will be a whole other lecture on networks and connectivity later in the course. Well, first of all, white matter is 45% of the human brain. Okay, so it takes up a lot of space, all those wires connecting one bit to another bit. And I would say we cannot possibly understand the cortex and how it works, or any little piece of it, without knowing the connectivity of each piece to each other bit of the cortex. Right? Imagine trying to understand a computer or a circuit without being able to see the connections between the bits. Like, it would drive you crazy. That's the situation we're in now in human cognitive neuroscience. It frankly drives me insane, but that's where we are. Next thing, the long-range connectivity of each little bit of cortex, some little bit right there in my brain, is connected to some bunch of other remote regions in my brain. And that particular set of connections is distinctive for that patch of cortex. So you can think of it as a connectivity fingerprint of a patch of cortex. Okay, so one of the ways that the different bits differ from each other is by way of their connectivity fingerprints. And I'm going to skip the rest of these because we're going to get back to them later, and I'm going to run out of time. And I'm going to assign the TAs to sound the gong at 12:15. Okay, good. All right. Now we're up to the cortex. This is really laughably shallow, but whatever. That's what we're doing here. So here's this cortex, and as I mentioned, it's a whole big sheet, and the different bits look really similar if you just look at them or slice them up. So how are we going to figure out how this thing is organized? Well, okay, now we're up here talking about cortex. All right. Let's start with the easy parts, which you've already seen. You've already seen this up here. These colored bits, visual cortex, auditory cortex, somatosensory cortex, gustatory taste cortex, those bits are like the easy parts of cortex.